Item number 7. A finite sequence a sub 1, a sub 2 up to a sub n with n greater than or equal to 3 is said to be strongly unimodal if there exists an integer k with k greater than 1 but less than n, such that this long chain of inequality is satisfied. How many strongly unimodal sequences a sub 1 up to a sub 26 are there, which are permutations of the set containing the positive integers 1 to 26? Alright. From the given inequality, a sub k has to be the largest because if you observe, a sub k is greater than all the numbers to its left and all the numbers to its right. So a sub k has to be equal to 26. Now, we still have 25 remaining numbers from 1 to 25. And what remains to be done now is to divide these numbers into two sets such that one set is placed to the right of 26 and the other to the left of 26. Now we consider several cases. In fact, there are 24 cases, but I'll just tackle the first two cases since the other cases easily follow. For case 1, we only place one number to the left of 26 and the rest to the right of 26. To illustrate, let's show some of the possibilities. For example, we can have 1 to the left of 26. So we have 1 less than 26 and then the rest to the right of 26. So we have 26 greater than 25, 25 greater than 24, and so on, up to 3 greater than 2. Another example for this is 2 less than 26, 26 greater than 25, 25 greater than 24, and so on, up to 4 greater than 3, 3 greater than 1. Okay, so since there are 25 numbers from 1 to 25, we can choose any one of those numbers to be placed to the left of 26. So we can choose one of these 25 numbers in 25 choose one ways. So there are 25 choose one ways of selecting one number from the set 1 to 25 to be placed to the left of 26. Now for case 2, we can place any two numbers out of these 25 numbers to the left of 26 and then the rest to the right of 26. So case 2, we can place two of these numbers to the left. So as an example, let's take let's say 2 less than 3 and then 3 less than 25. 25 is greater than 24. I mean, this is 26. This is 26. 26 greater than 25. 25 greater than 24. And so on. Up to 5 greater than 4. 4 greater than 1. As another example, we can have 4 less than 5 and then 5 less than 26, 26 greater than 25, 25 greater than 24, up to let's say 7 greater than 6, 6 greater than 3, 3 greater than 2, 2 greater than 1. Okay, so we can do this in 25 choose 2 ways. So there are 25 choose 2 ways of selecting two numbers from 1 to 25. So these two numbers will be placed to the left of 26, and the rest of the numbers not selected to the right of 26. Okay, so now we see that for case 3, there are 25 choose 3 ways of doing this. And then for case 4, there are 25 choose 4 ways of doing this. Up to case 24, which has 25 choose 24 ways or possibilities. So the required answer is just the sum of all these numbers from case 1 to case 24. So we have the sum 25 choose 1 plus 25 choose 2 plus 25 choose 3 up to 25 choose 23 plus 25 choose 24. Okay, so obviously this sum is not in the option, so we have to simplify this one. There is an identity that can help us simplify this long expression. There is a combinatorial identity n choose 0 plus n choose 1 plus n choose 2 up to n choose n minus 1 plus n choose n. This expression is equal to 2 raised to n. Okay, so obviously we cannot directly apply this identity because in the given sum we lack the term 25 choose 0 and 25 choose 25. So let us manipulate this expression or sum slightly so that we can apply the combinatorial identity. Okay, so this one is the same as 25 choose 0 plus 25 choose 1 plus 25 choose 2 up to 25 choose 24 plus 25 choose 25 minus 25 choose 0 minus 25 choose 25. So now we can apply the given identity to this portion of this sum so that we get 2 raised to 25 minus, take note, 25 choose 0 is just 1. Similarly, 25 choose 25 is also 1. So we have 2 raised to 25 minus 1, which is equal to 2 raised to 25 minus 2. So this is now the simplified answer. So the correct answer in this item is answer choice A. Item number 8. A square of side length 1 and a rectangle of length 34 are inscribed in a semicircle as shown below. What is the area of the rectangle? So we already have the length of the rectangle, which is 34. So we just need to find the width of the rectangle. Let us denote the width by W. Now we can easily find the value of W if we know the radius of the semicircle. So let us find first the radius. To do this, I'm going to connect the center of the semicircle to this point to create a radius. Now, we have a right triangle with a base of 17 plus 1. Because the center is exactly the midpoint of the longer side of the rectangle. So, since the entire thing is 34, this one right here must be 17. This one right here is also 17. Since the square has a side length of 1, the altitude or height of the right triangle must also be 1. Okay. So now let's denote the hypotenuse of this right triangle by r, the radius of the circle. So now we can just solve for r by using the Pythagorean theorem. So we have r squared equals 1 squared plus 18 squared. So r squared is equal to 1 plus 324, which is equal to 1 plus 324 is equal to 325. So r squared equals 325. Getting the square root of both sides, we have r equals 5 square root of 13. So the radius is 5 square root of 13. Now let's connect this center to this point to create another triangle, right triangle. Since this is also a radius of the semicircle, this one is also 5 square root of 13. Now we can solve for W. So again, by applying the Pythagorean theorem, we have the square of 5 square root of 13 is equal to 17 squared plus W squared. So we have the square of 5 square root of 13 is that's 25 times 13. That's 325. 17 squared is 289. And then plus W squared. So W squared is equal to 36. So W must be equal to 6. Now we can find the area of the rectangle. So the area A of the rectangle is just 34 times 6, which is equal to 204. So the area is 204 square units, and so the answer is answer choice A. Item number 9. A palindrome is a number that reads the same backward and forward. If a palindrome between 100 and 1000 inclusive is chosen uniformly at random, what is the probability that this number is divisible by 11? Let us determine first the number of palindromes between 100 and 1000. Clearly, the palindromes in this range are 3-digit numbers, so the units digit and the hundreds digit must be the same. Thus, we are counting 3-digit numbers of the form ABA. And obviously, A can take the values 1, 2, 3 up to 9. And B can take the values starting from 0 up to 9. Now, before we proceed to the solution, let us look at some examples of these 3-digit palindromes. If A equals 1 and B equals 0, we have the palindrome 101. Now, if A is equal to 2 and B is equal to 3, we have the palindrome to 232. Now, if you're going to count the total number of palindromes, we just have to multiply the number of options for A and the number of options for B by the fundamental counting principle. So, the total number of palindromes between 100 and 1000 inclusive is just 9 times 10 equals 90. So there's a total of 90 palindromes. Okay, now how many of these 90 palindromes are divisible by 11? By the divisibility rule for 11, the number ABA is divisible by 11 if 11 divides A plus A minus B, or equivalently 2A minus B. Right? Now, let's determine the lowest and the highest possible value for 2A minus B so that we can just limit our checking of the values of A and B. Now, the lowest possible value of 2A minus B occurs when A is equal to 1 and B is equal to 9. So, the minimum value of 2A minus B is negative 7. This occurs when A is equal to 1 and B is equal to 9, while the max value of 2A minus B is 18. This occurs when A is equal to 9 and B is equal to 0. This implies that 2A minus B is divisible by 11 if it's equal to either 0 or 11. So you just need to check for which values of A and B 2A minus B is equal to 0 or 11, since only 0 and 11 are the only values between negative 7 and 18 which are divisible by 11. Okay, so let's make a table for that, though it's not necessary. So this is A, B, 2A minus B. Okay, so is it possible to have A equals 1? So if A equals 1, B must be equal to 2. Because if A equals 1 and B is equal to 2, we have 0 as the value of 2A minus B. And 0 is divisible by 11. Now, is it also possible to have A equals 2? So if A equals 2, B must be equal to 4. Because for this combination of A and B, 2A minus B is also 0. If A is 3, B must be 6. So that 2A minus B is 0. If A is 4, B must be 8. And 2A minus B is 0 for this value, or values of A and B. Now, can we have A equals 5? If we have A equals 5, 2A is 10. If 2A is 10, the maximum value of B that we can have is 9. 10 minus 9, that's 1. 1 is not divisible by 11. Now, can we have 6? If A equals 6, then we can have B equals 1. Because 2A will be 12 minus 1, that's 11. Right? So now, can we have A equals 7? If A equals 7, 2A is 14. So B must be 3. So that 2A minus B is 11. Can we have A equals 8? If A equals 8, then 2A is 16. So B must be 5. So the 2A minus B is 11. Can we have A equals 9? If A equals 9, 2A is 18. So B must be 7. So that 2A minus B is 11. So these are the possible combinations of values for A and B, for which 2A minus B is either 0 or 11, or 2A minus B is divisible by 11. So of the 90 palindromes between 100 and 1000, there are 1, 2, 3, 4, 5, 6, 7, 8 palindromes which are divisible by 11. So the required probability is 8 over 90, which is equal to 4 over 45. So the final answer is 4 over 45, and that is answer choice B.